Greetings, welcome to Introduction to Linear Regression, Correlation and Residuals, Part 3. So we're going to go straight to a problem here. Let's go ahead and take a look at it in the textbook, and then we'll go back over to RStudio with it. And it's guess the correlation with Eduardo and Rosie. They're both collecting data on a number of rainy days in a year and the total rainfall for the year. Eduardo records rainfall in inches and Rosie in centimeters. How will their correlation coefficients compare? So we're making an assumption here that they're both collecting the same data. It's just that one of them's collecting it in inches, Eduardo, and the sane person, Rosie, is collecting it in centimeters. So how would that affect the outcome? Okay, well, I've already typed in my answer. If you don't mind, I got a little ahead of you here. Is their correlation coefficient would be the same since the correlation coefficient is unitless. We said that actually in the previous parts of this lab already. Okay, let's go take a look at 714. The next problem we want to look at is a study conducted in the University of Denver investigated whether babies take longer to learn to crawl in cold months when they are often bundled in clothes that restrict their movement than in warmer months, which is reference 18. That's what that number references there. Infants were born during the study year were split into 12 groups, one for each birth month. We consider the average crawling age of babies in each group against the average temperature when the babies are 6 months old. That's when babies often begin trying to crawl. Temperature is measured in degrees Fahrenheit and age is measured in weeks. Okay, so let's go over to the whiteboard and let's go take a look at that picture. So what does the picture look like here? That's the graph right there. Okay, so now they have some questions for us. Let's go back just real quickly to RStudio here. They say describe the relationship between temperature and crawling age. All right, well, what would temperature versus crawling age look like? Well, it seems if we were to look at this little drawing they gave us here, it appears that if we came in and just kind of eyeballed a regression line, that it would look not quite unlike, but similar to maybe that, or perhaps I'm a little low there, maybe up a little bit higher. You know, could be that it was more like up in this neck of the woods, you know, trying to put it in my hands. But the reason I'm pulling it down is because there's a possibility of a outlier drawing it. We notice that the clump, most of the stuff is up over in this neck of the woods, but we see that there is a couple of data points that are away from, in particular, this bad boy right here. We see that that data point right there has been moved away from the rest of them. And what that infers to us is there's the possibility of that being an outlier, okay? So what that tells us is that the relationship, and as far as I can tell, that there is a moderate relationship there that is linear, and it's also in the negative direction. And it does appear that there's an outlier around, oh, I don't know, what temperature would you say that that's at? Say around 40 degrees Fahrenheit and somewhere around crawling age of 30-something months. Now, it's easier once you've created your regression line actually to determine whether or not there's an outlier in your system, because then you're going to be able to have all the calculations of the residuals, and the residuals really would drive something as to whether it's an outlier or not. Okay, so the basic response, what we would want to type up in RStudio here, let's come back over here as we describe the relationship here. It looks like we have a moderate linear fit with some outliers. I think that's the best way to describe it at this point. Okay, when we get a little more fancy, when we have a little more skills under our hood, we'll be able to say a little bit more about stuff like that. Okay, so how would the relationship change if the temperature was measured in degrees Celsius and the age was measured in months? Well, this is the exact same thing that we just saw up above with Eduardo and Rosie. It would not change. Why would it not change? Well, because the correlation coefficient is unitless. And that means it's not affected by the units, okay? All right, so I want to talk a little bit more before we answer the next question about what the correlation coefficient is. So let's go back over to the whiteboard for a moment. Go back over here, and let's go just take a brief moment and let's talk about the correlation coefficient. So if we take a look at these different drawings that we have here with different scatter plots, we see different levels of the correlation coefficient. And we also noticed something else about it. Is if I came in here and I was actually to try and draw in my, hand by eye again, I'd see that this particular one has, while the relationship is weak, there's lots of air. In other words, my residuals are really large here. It does appear that the slope of the line on all of these ones up here, the slope is positive. So I'm going to rely upon your previous coursework in mathematics to remember the slope of the line is positive when the line is moving upward as we move from the left to the right. And so we notice the same thing here. The slope is positive, the slope is positive, and the slope is positive, okay? But we also notice is that as the residuals shrink, in other words, the air terms get smaller and smaller, the correlation coefficient gets larger and larger. Same song, second verse, but in the other direction. So now, notice in all of these that my regression lines, if I drew them in by hand, all have a negative slope. Okay, so in the case of these second ones here, our slope is negative. And again, what we notice is that the correlation coefficients are all negative. So when the correlation coefficients are negative, the slope of your line will be negative. If the correlation coefficients are positive, then the slope of your line will be positive. That's a nice, easy relationship to keep in mind. And we also see that, again, as the residuals get smaller and smaller as we move from left to right here, that the fit becomes more perfect and the correlation coefficient becomes closer and closer to -1. All right. So a few facts about the correlation coefficient. It measures the strength of the linear relationship. By the way, this is all really good stuff to have in your comp book. So correlation, which always takes values between -1 and 1, describes the strength of the linear relationship between two variables. We denote the correlation coefficient with the letter R, okay? So down here I got another set of them just to keep you, if you have a cloud of gnats, then your correlation coefficient is probably going to be very close to 0, right? So in this case we're saying the correlation was 0, all the way down to here where the correlation was 0.99, which means you're starting to fall all of the points perfectly on the line. So if R is equal to -1, then we have perfect positive or negative correlation, okay? So that's perfect negative correlation, which means all of the points, if we go back to our previous slide here, means that all of the points fell exactly on the line, okay? And similarly, if R was equal to +1, then we have a positively sloped line, and everybody fell exactly on that line. So R equal to a +1 means that we have perfect positive correlation. Again, that's two things that you ought to have in your comp book. So notice the correlation coefficient R, if we think about this in terms of an inequality, it's going to be less than or equal to 1, or it's going to be greater than or equal to -1. It's trapped between those two numbers. Okay, so let's go back over to our studio here, and let's go take a look at the last problem that we're going to work in this lab. And that's the correlation. Oh, sorry, my bad. Excuse me. I got one last question to answer in this one before I go on to the next one. Okay, the correlation coefficient between temperature is in Fahrenheit and age is in weeks, and R was equal to negative. Excuse me, there should have been a negative in there. There's a typo in there. Sorry about that. -0.070, because we saw that we had a negative relationship, right? If we converted the temperature to Celsius and the age in months, what would the correlation coefficient be? Okay, based upon our previous discussions, R should still be equal to what? Let me go ahead and put them in dollar signs again. So R would be equal to -0.070. In other words, the number would not change, okay? All right, let's switch on now down to the last problem for this lab, which is 718. Correlation coefficient part 2. Okay, so in this particular activity in 718, they're asking us to take a look at the following. It says, what would the correlation coefficient be between the annual salary of males and females at a company if for a certain type of position men always made, and this is the key thing here, this is the tricky word of this, always, okay, always made $5,000 more than women, all right? So what that would say is that the pay for men, the pay for the men is going to be equal to the pay for the women plus $5,000. Okay, so what about part B? Let's go ahead and I'm just going to put some formulas in here to help make this make more sense. So 25% more than women, what would that be? Well, that would say that the pay of men would be equal to 125% of what the women make, right? So it'd be 1.25 times the pay of the women. So I'm just going to write down all of the little scenarios here, and then we'll come back and talk about the correlation coefficient on each one of them. Okay, and then last but not least, what if the pay for men was 15% less than it was for women? So 15% less would be what? Well, that'd be 85%, so we're 0.85 times the pay of women, although we know that that's not the case, but we'll roll with this. Maybe not, at least not in the United States, right? Okay, so what they want to know for each of these scenarios, right? They say, what would the correlation coefficient be? Okay. Well, all right, now here's the deal. What we're assuming is that there is a perfect relationship between each one of them, right? So that's the thing you gotta get. This is almost kind of a trick question, okay? Is because you'd think that maybe things would be changing, but that it says always. So that means that this is just like the equations that you learned in algebra. All of the data points are going to fall on the same line. So for each one of these scenarios, and they're kind of trying to mess with our heads here, the coefficient, the correlation coefficient, that doesn't need to be capitalized, sorry about that, R equals 1 for all cases. Now, why is that? Well, the thing is that you got to realize is that the correlation will be exactly in 1 because each of our mock data sets, or each of our mock scenarios here, are fixed. They're what we call deterministic. In other words, you give me a pay for the women and it totally predicts what the pay for the men is going to be. In the real world, that is not the way it works. This is more respect, excuse my stuttering tongue there. This is more to respect of what we learned back in algebra. In other words, you give me a number for an x and it'll give you back a y. Well, what we've seen is working through this lab is that in the real world, that's not how it works, is that we get data and we try and find that perfect model to fit it, but we know that that model is not going to be perfect. In other words, it's not going to fit our data exactly, okay? All right, well, hopefully I didn't muddy that up for you too bad. If you have any questions, of course, on anything that we've done in this lab, don't be shy about posting it to Questions for Instructor.